Hello, everybody, and welcome to this month's News from Hubble and Across the Universe with Dr. Frank Summers. My name is Tony Darnell, and I work at the Space Telescope Science Center, and this is another of our monthly chats with an astrophysicist from the Space Telescope Science Institute, namely Frank Summers, who takes a lot of time and trouble each month to gather up some interesting stories, not only about Hubble that involve Hubble, but that are maybe other missions in other areas in astronomy. So before we get to that, though, I have a couple things I want to remind you of. If you are wanting to create a video in appreciation of the Hubble Space Telescope and you want to enter the Ode to Video contest, time is running out. They will close submissions tomorrow. So the clock is ticking if you want to make a video that shows your appreciation from Hubble. The rules are simple. All you've got to do is make a video about Hubble. It has to be less than 3 minutes. Other than that, you can use your creativity. And they have 2 categories for you to enter in. Those under 25, the so-called Hubble generation, you're special because you don't know a world without Hubble. And then there's another category for over 25, and that's the rest of us. And I barely make the cut. I'm right at 26, so I would have to do that second category if I was allowed to enter. So, and also if you entered the contest, you're going to want to join us for tomorrow's hangout. Georgia Bladen, the Hubble social media person at the European Space Agency, is going to join us for the first 10 minutes of the hangout to show us how the crowdsourcing voting is going to start. It'll start tomorrow afternoon sometime. So you'll want to check that out to learn how the voting will go. So that'll be tomorrow. Also going on during the Final Four March Madness stuff that everybody latches on to, we've started our own contest called Hubble Mania, and the link to that is in the description box below. We invite you to vote for your favorite Hubble images, and the winner will be announced sometime, I think, in April 6th to coincide with the Final Four championship. So that's going on also, and we encourage you to play along. The link is at hubble25.org/go/HubbleMania. Finally, with Frank here, I want to invite you to ask us questions and comment to us. We really enjoy the interaction, so we hope you'll leave us questions using the Q&A app. You can also leave comments on Twitter using the Hubble Hangout hashtag. That's what I'm looking at, as well as commenting on the event page on both YouTube and G+. So please ask us questions, and toward the end I will read them out to Frank, and he will get at it because he is an astrophysicist. So let me introduce him. Dr. Frank Summers, welcome back, Frank. It's good to see you again.
Hey, Tony. It's always great to see you.
Yeah. And, so I gotta ask you real quick.
Okay, go ahead. Go for it.
Astrophysicist, astronomer. Which do you prefer?
I actually was just about to do that because you made the point of he is an astrophysicist. Well, so the story is that Neil Tyson and I were up at the American Museum of Natural History, and we were talking about how do we bill ourselves since we are astronomers. I mean, astronomer and astrophysicist are really the same title. All right. If you wanted to split hairs, you might say the astronomer is the type of person who goes out and goes to the telescope and makes observations, whereas the astrophysicist is more the theorist who sits and works on computers and does equations, etc. But we chose that we would introduce ourselves as astrophysicists for one simple reason. No one has ever mistaken an astrophysicist for an astrologer.
Ah, yes. Doesn't that bug you? It bugs me too, and I'm not even an astronomer. I remember going.
How many times we were at Berkeley, we would get letters addressed to the Department of Astrology.
Yeah.
So the thing is, if you call yourself an astronomer, people sometimes will go, "Oh, I'm a Virgo. What does that mean, huh?"
Yeah. I even get that too. I'm not an astronomer, of course, but I say I work in astronomy, and they do the same thing. You know, they go, "Well, so what does it mean that I'm a Virgo?" And I'm like, I don't know.
It means you belong with a cluster of galaxies.
Yeah. Yes, exactly. So I see the point. Yeah, and you're right, because Neil deGrasse Tyson does do that too. He differentiates himself as that. I always thought it was because it sounded cooler.
It does sound a little cooler, but it also sounds a little pretentious. So I try to use astronomer when I'm with a group that I know understands what the term astronomer means, so I don't sound like I'm pretentious. But for the general public, the term astrophysicist is one that we can use and know that they recognize that, hey, we're a scientist, we're not a pseudoscientist.
Okay, well, we got that out of the way, so there you go, folks. It's all cleared up. Okay, Frank, so I know that you take a lot of time Oh, Judy left a Q&A here. CNN said astronomist in a recent article. What's that? An astronomist. That's right.
Okay.
I've heard that too.
We'll work on that. Thanks, Judy.
Okay, so what do you got this month, Frank?
Okay, so news from the universe for March of 2015. All right. So I got to warn you, Tony. We got some cultural references in this month's episode. Okay.
Cultural references.
We're going to have some fun with it. The beginning with the title of our first story is a series of fortunate events.
Oh, you mean bad puns or what we got?
But it's also a cultural reference because if you don't happen to know the books, it doesn't really make much sense. So
that was a series of children's books, right?
Yes, it's actually on my next slide. I brought it up.
Go.
It's called A Series of Unfortunate Events by the author Lemony Snicket.
Yes, okay, I remember
and
that.
it starts with book 1, which is The Bad Beginning, and finishes with book 13, which is simply called The End. So that's the series of unfortunate events in which all these crazy things happen to this kid. I actually didn't read these when I was a kid. Did you?
No, but my boys did. My boys read them.
Exactly. You know, my kids read through some of them. I know my son read through some of them. It wasn't around. I don't know whether it was around when we were kids. Of course, they must have been around when you were kids because you're just above that age line, right?
Yeah, I'm not quite sure. I mean, I did see the movie when it came out.
Anyway, so that's the book reference, but the series of fortunate events we're, of course, talking about the Dawn mission from NASA.
That's right.
An amazing mission that actually went through an amazing number sequence in order to get to the asteroid Ceres. So here is the plot of the series of the various orbits that Ceres was in. All right, and so the first one is the launch in September of 2007. That's 8 years ago, almost 8 years ago. And so that green line here, this is Earth's orbit. And then it moved into this orange orbit that crosses the red orbit, which is Mars. Okay, and it went through a boost from Mars in February 2009. And then it shifted to this green orbit. Okay, and this green orbit is Vesta's orbit, and it went along with Vesta, the asteroid Vesta, for 14 months, and then it shifted to the purple orbit, which is Ceres' orbit, where it arrived just this month. So these are the various orbits it was in, and here, by the way, are the transitions from it. So what they did is they added these light blue lines showing where it was thrusting, and then the little brown segments of those light blue lines are when it was coasting. So what you can see is that the Dawn mission has been thrusting for most of its lifetime when it changes orbits. It gets onto these orbits, and then it's almost in continual thrust as it goes in the changes between orbits. And that's actually something that's going to play off important later in the story. So it has arrived at Ceres. So here is a visual inspection of these things. Here is the launch in September 27th, 2007 aboard a Delta rocket. And this is like an amazing shot just after their initial engine burn and you starts to go up off the launch pad. Then in February of 2009, this is the artist's conception of it going past Mars. But while it was at Mars, it was able to take some cool pictures. Here is one of the cool pictures. You can see it passed close enough to Mars to get a gravity boost, a gravity assist, and close enough to be able to take images like this. So it can go on and see the detail in some of these craters upon craters upon craters here on the surface of Mars. So then after getting the gravitational assist from Mars and, of course, more thrusting, it arrived at Vesta in July of 2011, and it stayed with Vesta for about 14 months, from July until September 5th, 2012. And this is a composite image of the asteroid Vesta. And I guess I should have put up the HST image for comparison.
Right.
The best image we had before this is the HST blobby image, right? You know that image.
Yep.
And we looked at that HST blobby image. We could tell it wasn't a sphere, but were there some major craters and such? And this is just so amazing compared to the HST image. So now we have a good look at the second largest object in the asteroid belt. Okay, so that's the full composite model of Vesta, and then it boosted and has just on March 6th of this year, what is that?
Last week.
5 days ago, last Friday, it pulled into orbit around Ceres. All right, and so we had a big announcement from NASA on Friday, and here is one of the animated GIFs that they released that day. Ceres has a new home, the dwarf planet Ceres. You will note that I don't like to call it a dwarf planet because I think the phrase dwarf planet doesn't mean much of anything. It just means a big spherical asteroid, right? Any asteroid that's big enough to be spherical would be called a dwarf planet. I prefer to think of the families of the solar system, the asteroids and the Kuiper Belt objects, instead of trying to call individuals of those dwarf planets. Doesn't mean much to me.
Yeah.
All right.
That's a good point.
Anyway, so here is, I'm going to take that animated GIF that you just saw there, slow it down, and show you what Ceres looks like according to the current imagery of it. Now, as I said, for most of its transitions between these orbits, the Dawn mission is thrusting, and it can't take observations while it is thrusting. So these images are taken only at times when they decide, all right, we can stop the thrust and we can take more images.
Why is that? Is that because of the vibration or what?
I don't know. I was reading, just reading on the website. One of the reasons why they don't. I was expecting a lot more images of Ceres to come out during approach, and we just got these little dribs and drabs, and I was trying to figure out why. And they said, they have stopped the thrusting in order to take the images. Maybe they have to reorient the spacecraft in order when they do the images, and so that the thrusting would
maybe that's it.
Yeah, would interfere with it. So they only got some pictures. So here is one, and this is a rotation. So we're just going to look around, and what do we look like, Tony? We got what we see on lots and lots of objects in the solar system.
Looks like
lots
a moon.
and lots of craters.
Yeah, lots of craters.
It's gray and white with lots of craters. But there's one really cool feature that we've noticed already, and it's right up in here, inside this crater here. We got these two bright white spots. Now, at first, we weren't sure whether those bright white spots were a detector artifact or something wrong with things, but we've taken multiple images of it. Yes, this is a real image. This is a real feature. There are two bright white spots on the surface of Ceres, and so we're really excited to find out what those are. My guess, if I had to say, all right, I just wanted to throw out something, and would be like, all right, so maybe something is smashed into Ceres in the recent past, and you've got bright snow revealed because of an impact, perhaps.
Right. Somebody dropped a compact mirror there, and that's a mirror reflecting back. One of the two. I think you may be more right.
Yeah. What it most likely is some process has exposed fresh snow. Okay, there is fresh water ice or carbon dioxide ice based on the surface of Ceres, and it has been exposed. But we won't know for a while. Why? Because although it is now captured by Ceres gravity, it is not in what is called a science orbit. Okay?
You mean Dawn. Dawn isn't.
Dawn, yes, Dawn is not in its science orbit. Okay? So here is where it was on March 6th when it got captured, when they said, okay, now we are captured by Ceres gravity. But it is going to continue to make maneuvers. It's still going to thrust. And on March 28th, it will have made effectively a U-turn and start heading in closer to Ceres. And let me just say that the size of Ceres is exaggerated in these diagrams. It's really it's significantly smaller than is shown here, of course.
Okay.
So it's going to make a U-turn, and then by April, it's going to fly up and over and start into an arc that will lead into its what they call the science orbits. All right, and throughout April and into May, it will begin its true science observations as it gets into that circular orbit you see there around Ceres. So Dawn science, although it's in orbit around Ceres, it's also on the outside of Ceres. It's on the night side of Ceres, so it won't be seeing much of the lit side of Ceres for a while. We won't get really good observations from the Dawn mission until April, and it gets into what they call the science orbit here. Okay.
Okay. Let me interrupt you for a quick second, Frank.
Sure.
Zigzag on the Q&A app is asking, are there any IR images of the bright spots?
Infrared images, not from Dawn that I've seen.
Yeah. Okay.
Okay.
I just wanted to, since it was relevant to what we're talking about, I wanted to interrupt you with that.
Okay.
Is Ceres is it spinning?
Yes, it has to be spinning. I do not know its rotation.
Okay, but it is spinning. So whatever orbit they pick for Dawn, they could if it's in the as long as it stays out of the dark the backside there, it would, you know, you can still image the whole thing. There's nothing that's going to miss, I guess, is my point, right?
Right. It's going to be with Ceres for about 18 months. I couldn't find the exact end date. Maybe there isn't an exact end date because it's not going anywhere else. Okay. It's in orbit around Ceres. This is its final home.
Sure, it's where it's going to be.
Okay, so it's going to be in orbit, and it will last as long as it lasts, perhaps. But the one comment I read about it said that it's going to be there for 18 months, and so they will map every bit of Ceres in great detail, just like we got with Vesta. So the fuzzy images from Hubble have already been eclipsed with Ceres, and then we're going to get a full surface map in great detail when we get down to the science orbits. Okay?
Cool.
All right. That's story number one. We have our second story, which I call Thrown for a Loop. All right? And actually, it really fits in with that last diagram because this looks something like what we just saw. If you'll sort of look along here and you see this swoop along here and then this sort of loop around here, that looks a little bit like, you know, the orbit that they're going to do around Ceres, right?
You spend too much time looking at astronomical images, Frank.
And of course, it's not an orbit around a asteroid or dwarf planet. These instead, this is the digitized sky survey image from the Palomar Observatory Sky Survey from NGC 7714 and 7715. All right. Unfortunately, these galaxies don't have a fun name, but we could call it the loop-to-loop galaxy. Okay. So here we've got a loop-to-loop galaxy. All right. I want to see that on the internet someday. Okay. I want to say Tony and Frank in their hangout.
We'll let the IAU know.
Nicknamed it the loop-to-loop galaxy. All right. But you can see that you've got this sort of circular feature in the galaxy on the right, which is 7715. Right, and I always like to provide these context images because you get to see what the ground-based observatories. And here is the image from the Sloan Digital Sky Survey, so another ground-based survey, but with better resolution, more colors. Okay.
Yeah.
And you can really start to see that the colors are different here. So Hubble looked at this, and this is just this is what we call one of our image releases. It's one of our pretty pictures. It's really cool. It's taken for some science, but the image is not released with a science result. It's really just released to say something really cool. And we didn't look at 7715 over here on the left. Sorry, 7715 lovers. We didn't get that. Instead, we got a great resolution of 7714 over right here. So we only got the loop-de-loop part of this galaxy pair. And here is that image of a galaxy NGC 7714.
It really is striking just how crystal clear the Hubble images are. It just blows me away every time. The ground-based just can only do so well because of the atmosphere. It's not the telescope's fault. It's just where it is.
Right, and we do this in the Worldwide Telescope software. We zoom into great detail onto an image, and then we crossfade from Hubble to ground-based and back to Hubble. And it's just, wow, impressive. Like, oh.
I'm glad you brought up Worldwide Telescope. Let's just remind people, this is some free software developed by Microsoft that you can download and play with not only data sets like this, but you can create tours and your own little videos with it too. It's worth looking up. Google Worldwide Telescope and play with it. It's a lot of fun.
And Tony, may I mention that Microsoft Research has just recently open sourced the project?
That's by all means. Let's mention that.
They're in the process of open sourcing Worldwide Telescope. Microsoft Research developed it. They got it up to, I guess, version 5.1. And so there's a 5.1 gold release, which is the last release that's going to come from Microsoft Research. and any further releases are going to come through an open source project. So it's technically now called Open Worldwide Telescope, since, you know, if you're going to put it out in open source, you got to add that open on it to make sure everyone knows.
Yeah,
Right.
if you love computers and astronomy and visualizations, it's really something to look into. You will have a lot of fun. And we should have brought it. I wish I had remembered this when with the Ode to Hubble video contest. That would have been something you could have used maybe. So anyway, check it out. That was great. Glad you brought that up.
All right, so let's take a look at this galaxy just a little more, because you can see that that sort of circular feature here, all right, is due to the galaxy interaction. And it doesn't just end here, but you look at this, I don't know if you can see this very faint tail swooping on out there. So the galaxies have obviously collided. They've made an interaction. But in doing so, they've produced an amazing, you know, swoop of a tidal tail that it's not something you see in a lot of galaxies. I mean, we see these big, long, arcing tidal tails that, you know, just stretch off in one ring. But a looping, swirling tidal tail, sort of a corkscrew tidal tail, okay, that's actually quite unusual.
Would that be maybe due to the rotation of the galaxy itself as it interacted with the other one? Maybe it kind of flung them out in that circular pattern?
Yeah, no, it's got to be an off-axis hit that invokes some sort of torque to things. But between the two, it's probably an interaction between relatively equal mass galaxies, simply, or there could be a third galaxy involved here.
Wow. Now those are all stars, right? In that tidal stream.
What you're looking at here is stars.
Think about that, folks. Those are stars in there. All of that, it looks like a big cloud of dirt and dust and all that. Those are stars.
Well, the dark brown stuff is, of course, the dark brown stuff that you can see up in here, right? That, of course, is going to be gas and dust. Along in here, it's glowing and such, so that's generally that's going to be stars.
Yeah, that's the part I'm talking about. That right. Brownish. What
we really want to look at is, you were talking about the resolution of Hubble. Well, see in here, see these bright blue regions in here? Let's actually go to full Hubble resolution on the next image. So there you go. See, I wasn't showing you everything Hubble had. This is full resolution at 1280 by 720. And you can see these bright blue regions in here, these super star clusters. This is one of the things that Hubble's been really good at over the years, is looking at these galaxy collisions and seeing the induced star formation during a galaxy collision.
Induced by the interaction, correct?
Exactly. So the gravity of the interaction causes these giant gas clouds to collapse and start producing stars at a prodigious rate. Right? Hundreds to thousands of times more stars per year than are produced in a normal galaxy.
You know what I always think of? Tell me what you think of this analogy. You know how you go to some places in the coast of Florida or whatever, you swirl your hand in the water at night, and you see that phosphorescent algae kind of glowing as you do so. I always think of that when I think, if you take a galaxy and you just stir it really, really fast, all these stars start to ignite and start to burn. What is that? Is that a reasonable analogy?
It's a reasonable visual analogy, but I don't think that those algae are starting to phosphor because they're slamming together and gravitationally collapsing, and nuclear fusion is turning on the core. Fair enough. They could produce nuclear fusion. That would be really cool.
Okay, a visual analogy. I should have said that. Okay.
It does make a nice visual analogy, but the other thing that's a good analogy is that you are creating a disturbance in a circular pattern, right? And spirals, but the spiral arms of galaxies are these spiral disturbances. They're gravitational disturbances. You're making a wave disturbance, but it's still a gravitational, you can think of it a gravitational wave moving across, although I don't want to say gravitational wave because then that has a real connotation of gravity waves, but a density wave, how about that? So when we think of the spiral arms in a galaxy, it's more of a density wave across the galaxy, which is something like the wave that you're stirring up in that algae. But what I like to show about this is that you still have the core of the galaxy, and if we could see NGC 7715, it would have its core, but all of the stuff around it gets swirled and stretched and pulled into this big loop-to-loop pattern here. So one of the cool things about galaxies is they really do collide and create these new shapes. We can think about the idea of planets colliding or stars colliding, but you know what? the odds of that happening are incredibly, incredibly, incredibly small. It's never really going to ever happen. All right, there are scant places in the universe where star collisions or planet collisions could even possibly happen.
That's also a little mind-boggling, because from our perspective, we look at a picture like this, and it looks really, really crowded there. But we have to appreciate that the scales in between the stars are such that it's misleading a little bit. That there really isn't that much space in there.
Right. If you take the size of a star compared to the size of another star, the separation between them is about 1 billion times the size of the star. Whereas you take the separation of a galaxy versus another galaxy, the separation between them is, say, 20 or 30 or 50. Okay? It's tens of times larger for galaxies. It's billions of times larger for stars. And that's why galaxy collisions are frequently observed, and stellar collisions are almost never observed. Cool?
Yeah, very cool.
All right. Let's do our last story. And as I said to you last month, we're going to be doing some sequences on 25 years of Hubble. So for each hangout this year, what I'm trying to do is come up with a cool topic to tell you about what Hubble has seen over its history and sort of do a retrospective. Also because, with Hubble 25, we're doing lots of things where we're preparing information about what Hubble has done. And this month's topic is gravitational lenses. All right, so let's start at the very beginning, the idea of lensing. So here in the upper left, we have a light bulb. Here in the lower right, we have an eyeball. And in between, we have this glass lens, right? And so the glass lens acts to collect and focus light. All right, so you can see that if the light comes from this light bulb, passes through, is bent as it passes through this glass lens, and comes to your eyeball. Now, normally you would have another lens to bring it into focus, etc., but we're going to ignore that for now. But the basic idea of a glass lens is that it collects and magnifies light. Okay? Now, there is, in general relativity, the property that mass warps space. I think I've said that before with you, Tony, right?
I believe so, yeah. We mentioned it in other places too, but yeah.
We use that a lot, okay?
Yeah.
So the presence of the mass, like this star here in the center, warps the space around it, and then light traveling across that warped space changes direction as it passes the mass. Okay? So that light is deflected by the presence of mass. Okay? Moving forward one more step. Well, now we say, here we have, instead of that eyeball, we have the Hubble Space Telescope. Instead of that light bulb, we have a very distant galaxy. And instead of that glass lens, we have in the center a cluster of galaxies. Now, if you have an extremely massive cluster of galaxies, it's going to warp the space around it so much that it will act like a glass lens. That the light from this distant galaxy will be bent as it passes through that warped space, and it will then collect and magnify light just like a glass lens. Well, not exactly like a glass lens, because glass lenses are ground to be nice and smooth, and these gravitational clusters are generally very lumpy.
Yeah, this will be a very lumpy lens.
Yes, we're doing some lumpy lensing here. But the point is that instead of having glass, you have mass, and mass can act as a gravitational lens. Okay, so that's the educational setup for it. Now, what has Hubble seen with this gravitational lensing? Right? And it starts all the way back in 1990. This is one of the first images that we released from Hubble, and it's gravitational lens G2237 plus 0305.
Oh, yes, remember well.
Ah, yes. Well, I was at where was I? I was at Berkeley at the time, okay, and this image came out, and everybody was stunned, right? Because no ground-based telescope can see this. All right, what you have here is that fuzzy blob in the center is a nearby galaxy. It's about 400 million light years away. So nearby is on a cosmic sense, okay? 400 million light years, you have a galaxy. Then you have these 4 bright spots. All right? These are images of a quasar that's 8 billion light years away. So 20 times more distant than the galaxy. But the two are lined up so exactly from Hubble's point of view, from Earth's point of view, really, that the mass of the galaxy acts like a lens and splits the light into 4 separate paths. So there are 4 pathways around the mass of this galaxy that produce images of that quasar. And this is what we call an Einstein cross. All right, and this was one of the very first images, and it was just amazing because we knew that there was a quasar shining through this galaxy. We didn't have the detail to be able to see and make out these 4 individual images until Hubble went up there. And in fact, this was Hubble with the flaw in the mirror, right?
That's right.
90.
That's right.
Even with the flaw in the mirror, Hubble had better resolution than any other telescope and allowed us to see an amazing shot of an Einstein cross gravitational lens. Okay? Next image I got for you, 1995. The Galaxy,
I remember this one.
Yes, the Galaxy Cluster Abell 2218. And this was another one where this was after servicing mission 1, when we had the Wide Field Camera 2 in there, Wide Field Planetary Camera 2 in there. WIFPIC 2 enabled us to get the fine resolution that Hubble was designed for, and it's really cool to see all these galaxies, and then all of these streaks and arcs are the gravitational lenses. All right? These are galaxies on the far side of the cluster coming through this lumpy lens and becoming stretched out into these streaks and arcs of gravitational lensing. All right? And so this was the 1995 image, but we also released a color version of this in the year 2000. This was part of our servicing mission 3A, back to Hubble's Back in Business press release. So I like to show both the black and white and the color to show that, well, even when you do have a color image, it doesn't have that much color because
there's not a whole lot of variation there, is there?
Most of the elliptical galaxies are just these yellow blobs. But it does bring up something cool, like this orange arc here, this gravitationally lensed arc here that's orange, and this galaxy here that's blue, and there are a couple other small blue things. But you can see that galaxy clusters are mostly filled with these big yellowish elliptical galaxies. All right. So this is one of the most prevalent gravitational lensing images. But I have to say the most amazing gravitational lensing image I think we've ever gotten is this cluster, the cluster Abell 1689. Now, you're talking about Hubble resolution, right?
Yeah.
This image is 4,000 pixels by 4,000 pixels. So I don't care what computer monitor, unless you've got a Quad HD monitor on your desktop, you're not seeing this, because you're still not seeing it because YouTube isn't giving it to you at Quad HD. So there is incredible amount of details, and the personal story I have about this one is that at the time I had the visualization wall in my office, and the visualization wall was a bank of 16 monitors, each 1280 by 1024, so that the resolution was 5,000 by 4,000 pixels. And it was built just to examine images like this, so that you could take these images, put them up on this bank of monitors, and be able to see them pixel for pixel and see all the details. So Mark Postman, when he got the data off of Hubble and had just done his first initial processing, came down to my office and we popped this up on the visualization wall. Unbelievable. Because
Mark is another astronomer at the Institute. Yeah.
Yes, Mark Postman is a very famous astronomer. He heads our community missions office these days, right?
And he's also involved in WFIRST as well.
Right, looking at future missions. Okay, so you can see these big long arcs here in the center, right? And you can see some tiny arcs moving out here. But if you really get the full 16 megapixel image, you can see small little streaking arcy things all the way out to the corners of this image.
Now I have a question. Those arcs you're talking about, they all seem to kind of go around a common center, or is that just an optical illusion? Like, if you kind of look at how they're sort of, arced around, they kind of seem to be arcing around a center.
And they are, and for the most part, they do.
Okay.
Which is a thing. So the center of the cluster is where most of the mass is concentrated. All right, the mass isn't distributed smoothly throughout. And then when I say mass, I'm not talking just the mass of the galaxies. I'm also talking the mass of the dark matter that you can't see, right?
Right.
So the dark matter will have its maximum concentration at the center of the cluster, and it will slowly get lower and lower density as it goes out. But you can also see this clump here in the, I guess it's the upper right.
Mm-hmm.
There will be an extra concentration there. And if you look really closely between this galaxy and this galaxy, you could actually see some of the arcs change their shape. They aren't circular around the center, they actually arc off differently. And that's one way to, by the shape of these arcs and where their centers are, tells us the mass distribution in the cluster. Since most of the mass is in this dark matter, by examining these lensed objects, we can actually measure the mass in this cluster, the mass distribution in this cluster. So on the next slide, I actually have some details from this, right? And we can see that you've got these big, long, streaky arcs things here. All right, here is in the upper center. You can see this one has a little bit of change in its shape, probably due to this big galaxy just to its left. You've got all these tiny things and all of the faint little detail that only Hubble can see. So this is one of the reasons why Hubble is so good at gravitational lensing, is it can see all these fine details of these gravitational lenses that telescopes from the ground can't see.
So because dark matter is the major contributor to this lensing, what you're really doing then, as compared to the stuff we can see, is you're really mapping some of the, you can infer where the dark matter is from this then.
Exactly. Right. And let me add one more point since that I like to bring up, and we have enough time to discuss it, is that we're not mapping the three-dimensional structure of the dark matter. We're actually mapping the two-dimensional structure, because it is the accumulated density along the line of sight that we're measuring.
Okay.
So if a cluster is shaped like a football, and you look at the football from the side, you're going to see one map. But if you look at the football from the end, you're going to see more of it. Okay?
Got it.
And actually, you'll get more lensing if you looked at the football from end on, as opposed to if you looked at the side on, right?
Oh, that's an important point. Yeah.
Right. So that is actually one of the worries we have in astronomy, is that we're biased when we find a lensing cluster. Are we biased towards clusters that are end on rather than sideways on? Because the ones that are end on will produce more lensing, and we'll notice them more, right?
Right.
So again, we have to look out for those systematic biases in our observations. Okay?
Okay.
So that's gravitational lensing with clusters, but then we have some really other cool effects, because I showed you an Einstein cross. Here are 8 examples of what we call an Einstein ring. Okay? Now, they aren't full rings. Actually, I think the fullest ring is this one down here in the lower right. And I'm going to call him Mickey. Why? Because I don't want to say that name. Whatever his phone number is there, okay?
2321209.
So we got a circle here for Mickey, and then Donald and Goofy over here. Goofy actually has almost a circle here, and then the other ones have some very strong arcs here, okay?
Mm-hmm.
And so these occur, again, when you've got a galaxy and a distant source that are almost exactly lined up. All right, from our point of view, they happen to almost exactly line up in space, and instead of just producing points like we did with the Einstein cross, those 4 points in the Einstein cross, you actually get it spread out. An almost perfect alignment will give you a gravitational lens, gravitational Einstein ring, almost a circular ring of the lens. That also requires that you don't have a lumpy lens. This requires that you have a relatively smooth lens. So, of course, you're only going to see this down at the core of a relatively smooth galaxy. And you'll notice
these examples you're showing, the foreground galaxy, it does look pretty smooth and uniform.
Right. You'll notice these are all elliptical galaxies that look relatively circular, relatively smooth, so that if you line up almost perfectly with the center of them, you can get this Einstein ring effect. All right? And this is extremely rare. This is extremely rare to have that kind of alignment, to have that kind of smoothness. But we got billions of galaxies in the universe, so if you look carefully at enough of them, you're bound to find a few. Plus, there are all sorts of cool things that happen with lensing, right? And so I'm going to show you a couple of fun ones. This is one that has been nicknamed the Dragon. And so if you look at, I forget the name of this cluster. It's probably got a phone number, and it doesn't have a nice name. But you can see that there's this big long thing up here that if we pull out, you can see it's got a head here that you can see almost, you really take a look and you can see the galaxy. It's a spiral galaxy. There's the core of the galaxy. You can see the spiral arms of the galaxy. But then it's multiply imaged, all right? Multiple images along this big long tail. I think there are, well, 1, 2, 3 different images of the galaxy. There might all in this one in this tail. There might be 4. I'm not sure. I'm not exactly sure. And it got the nickname the dragon, as if this is the dragon's head and here is the dragon's tail, such as you see in the Chinese New Year parades, with the dragon leading down the street and everything. So that's a cool one.
That's a really cool one.
Yeah, isn't that?
That's a smeared out, stretched out galaxy, and you can see the galaxy on both ends of it, kind of a little bit.
Weird. And that's the other thing. Is what I love about this is the dragon head really almost gives you an idea of like, ooh, that's almost a clear image of what that galaxy looks like.
Right.
All right. The second one we had is one from our age. We call this the Space Invader lens.
I remember that one. Yeah.
So again, you can see all these the gravitational lensing going on here. There's some streaks and arc in here, but up in this orange box blown out here is a duplicate of a galaxy. So here's the
but you know, Frank, the kids today, they're not going to know about no space invaders.
That's why I said there's a lot of cultural references in this talk. So here it is. For those of you who aren't
that is it. The Space Invaders game.
Those of you who didn't grow up in Atari in the 1970s, this is Space Invaders. I believe it earned more quarters in the 1970s and the 1980s than any other video game out there.
Wow, more than Pac-Man? That's a lot. That's cool.
Well, this was in the early days. This is so maybe it was the 1970s.
Black and white. So it looks like that second row from the top there is what it looks like.
Yeah, exactly. That second row from the top here. Comparison. All right. There you go. So if the kids out there don't actually know what Space Invaders was, here it is for you. You can see. And this is our Space Invader.
That game drove me crazy. It used to stress me out, especially when it got really hard. I just threw
but how good did you feel when you beat it, okay? When you beat the level.
I really did.
But they only gave you like 5 seconds to rest before you had to go and concentrate again. That's what made it.
I know.
Okay. And finally, we have one that we just recently released. You may have talked about it in a recent Hangout. Is, of course, our smiley-faced lens.
No, we didn't talk about it in a Hangout, but that was an ESA release, wasn't it?
This was a European Space Agency release. And actually, you know, our news group here didn't choose to co-release this one. Which I think was I think they found out that was a silly thing. So here we have our smiley face. We have our eyes and our nose and our mouth, and the other lenses make a head. All right. And did you know the best comparison of this one, Tony?
What?
It was to the Jack in the Box character.
Wow. It really doesn't look like that.
I saw this online and I was just like, wow, that's just... So for those of you who aren't Americans or don't know what Jack in the Box is, they have a guy with a snowball head and the smiley face to advertise this fast food restaurant called Jack in the Box, which I don't know. I used to see him in California. Do they have him here on the East Coast?
I haven't seen him. I've never seen him. I think they call it Jack now, and I think it might be around.
They may even call this character Jack, okay? But if you don't know Jack, we have a lens that looks just like him.
Yeah.
All right. So the final one is the one that we released just recently, talking about the. We're going to bring the whole thing full circle. An Einstein cross seen in a cluster lensing. And so this is sort of brings everything full circle, combines everything together because we have the cluster of galaxies. This is an MACS cluster, J whatever it is. And so you can see that we've got all this, but zoomed into this orange box, you can see around this galaxy we have an Einstein cross with these 3 yellow dots. All right? And of course what makes this one really, really cool is this is not a quasar as it was in the previous Einstein cross. This is a supernova in a distant galaxy. Yeah. And it's not just that it's happening in the Einstein cross, but you're getting multiple lensing upon multiple lensing. So here's the. Go ahead, Tony.
I was just going to add to that. We had the Hangout on this last week, and the astronomers said that it's still getting brighter. They haven't actually gotten to the point where that supernova has peaked.
Yep. So I mean, there's you're able to watch in real time, seeing the supernova change its brightness, and you have 4 different views that, because the way it passes through around that galaxy are 4 different times by the time it arrives to us. So we can actually see the brightening in one before we see the brightening in the other, and the third and the fourth. They are separated by different times. Plus, that background galaxy, so that's this down here, that background galaxy also gets lensed by the cluster in 2 other positions, and the light from the supernova would pass through those 2 other positions separately. Now, I believe the one in the center would have gone through about 5 years ago. Do you remember what?
Yeah, it was a few years ago, and the other one has yet to happen.
Yeah, and the other one's a few years ahead of now. So while we're seeing it happen right here in this version of it, all right, it probably happened previously. We didn't observe it in this other line of sight, and it will happen eventually in this other line of sight, which will give us really great measurements of the sort of the mass path length through this cluster. See what you're measuring. 2 important
things about that. First of all, you get to observe the same event more than once, measure it again to get really accurate measurements, like Frank said. But you also, because of the lensing, you're making Hubble more powerful. It could not have seen the supernova had it not been for these lenses. Isn't that right, Frank?
I'm not exactly sure on that one.
Well, that's what they said last week. So
okay, they said it last week. I will go with that.
Yeah. So that's what's remarkable about this whole lensing business, is that we're getting to see things. We're using it to our advantage to allow Hubble to see things that ordinarily wouldn't be able to see. And with this multiple lensing idea, you get to see it again. How do they? Well, I'll let you finish, and then I'll ask you a question.
Gravitational lensing gives us cosmic instant replay.
That's right.
How cool is that?
That is awesome. It's really kind of creeping me out. That's amazing how that happens.
Not only do we get 4 views of it here, we also will get some at least a 5th view of it over here when it comes through. So they're
able to calculate when that's going to be. Is that based on their model? They made a model of the gravitational lensing, and they can just kind of figure, well, based on that model, we should see it X.
Right. So the distances between the distant galaxy and the cluster, and from the cluster to Hubble, are easy to calculate. That's just geometry, right?
Okay.
That's simple trigonometry. And then it's how that light passes through the cluster as it changes its direction. That's the thing that they don't quite know. In order to get that, they have to have a mass model, right? And so getting the mass model to say how it bends through the cluster, but it's an iterative process, because you're using the lensing to determine the mass model, and then you're using the mass model to determine the time it takes to do the lensing, right?
Right.
So it's an iterative process. You come up with an iterative solution that sort of works really well to get it, and so it's pretty solid in those predictions.
Cool. Okay, I want to get to questions, Frank. So I'm not going to interrupt you no more.
No, that is my last slide.
Oh, that was it? Oh, perfect timing.
I just had the slide on the Hubble teach-in on April 24th, if we have any teachers watching.
Yes, I'll be creating the event. In fact, I've been getting email on that soon. So you'll be why don't you tell us a little about what it is?
Okay. So what we decided we wanted to do is we wanted to reach students and teachers in all 50 states for Hubble 25th anniversary. We do a lot of events for the press, we do a lot of events for just the public, but we really want to do an educational lesson about Hubble's 25th, the 25 years of Hubble, just for teachers. So we're preparing all sorts of special and cool things that have relationships to what teachers do in classrooms and how to present what Hubble has learned over these 25 years in classrooms. I'll be the main presenter. We may have other guest presenters where actually lots of people are going, ooh, this sounds cool, can we get involved? So there'll be lots of people saying, but the main thing that we have set is that it will be April 24th, Hubble's 25th anniversary date, 1 p.m. Eastern, so that it would 10 a.m. Pacific. And if you want to be in Hawaii, you can get up bright and early. I guess that would be, what time is it in Hawaii? Another 2 hours, 8 a.m. in Hawaii?
I guess something like that.
All right, so we wanted to choose a nice day. It's a Friday, so a good day to discuss Hubble and finish your week with the Hubble's 25th anniversary. If you want information, I may email to amazing-space.stsci.edu. We are in the process of setting up the webpage for all the information on this. It's about 6 weeks away.
Okay, and I would invite everybody to follow us on Twitter at Hubble Telescope. Also, like us on Facebook, and you'll learn about you'll get updates on it on our social media channels as well. Because as Frank and his team create the content for it, and if you're a teacher and want to participate, we'll make sure to get the word out to you. Okay, Adam Synergy on the Q&A app is asking a question here. Astronomers have recently found a strong gamma ray signal in the newly found Milky Way satellite dwarf galaxy Reticulum 2.
Wow, that's a very specific question.
Is this likely to be evidence of dark matter? The gamma ray signal, are gamma ray signals evidence of dark matter?
Gamma ray signals could be evidence of antimatter, right?
Yeah, they're high energy.
Yeah. All right. So first of all, gamma rays are the highest energy of electromagnetic radiation. They're above X-rays, right? From visible light, you go to ultraviolet light, X-ray light, and gamma ray light. So gamma rays require a very high energy event to create. Now, dark matter generally doesn't have much interaction with normal matter. It interacts via gravity. When you get a gamma ray signal, you're really thinking black hole or supermassive black hole type events. Accretion disks around supermassive black holes, where things speed up to relativistic velocities, you can get gamma rays from there. Supermassive black holes also emit charged particles at very extremely high speeds, and when those smash into things, they can do gamma rays. I don't see any strong reason why that would be evidence of dark matter, but it's evidence of high energy interactions. Okay.
Yeah, good question, Adam. So I think the answer would be not necessarily. Like Frank said, dark matter tends to be a gravitationally observed thing. So light rays, maybe if there was a gravity lens, a lot of dark matter in the middle there between us and the gamma ray source, maybe it would be lensed by that, but that would be about it. Julie Schmidt. Hi, Judy. What's that stretchy dragon galaxy? Why is that stretchy dragon galaxy so red? Red spirals are kind of weird, aren't they?
Okay, that's a really good...
Judy, I don't know about that.
That is actually a really good point, is that the spirals generally tend to be like yellow with cores with like ellipticals, and then they generally have the bluish spiral arms there. So what am I going to come up with here? Well, first of all, it would depend upon the filters that this image is taken in. Okay. This image, you'll notice that the elliptical galaxies themselves appear more red. So I'm going to guess that this image was taken with some infrared filters. All right. This is not an RGB image here. I think you're going to have one blue or ultraviolet filter here. That's where you're getting some of the blue galaxies there. I think you're going to have a red filter, and then you're going to have an infrared filter. So I think what appears red in here is not red, it's infrared. So inasmuch as the low mass stars are what's going to produce lots of infrared light, we're going to get the red here probably from the low mass stars in the disk of the galaxy.
A lot of the stuff in between the blue and the infrared is what we're missing, more or less.
I think we're missing a good amount of visible light. I'd have to check on this. This is Abell 370, now that I remember it. And I can go check the Abell 370 the web page for Abell 370 and see what the filters were. But I suspect there's a lot of infrared in this image. Okay.
All right, I'm going to go over to YouTube because I saw a comment or a question over there earlier. This one was up before we started, so I'm going to ask this question. I can't pronounce your name. I won't even try. But look at that name. At least you can see it, right? Because I have a question. Are there any galaxies pictured by Hubble but too faint for Hubble to measure its redshift?
Okay, great question. Absolutely. And we've got Zbigniew, right? Sleziona?
Yeah, Zbigniew. Yeah.
We used to have a famous guy in the 70s, Zbigniew Brzezinski, right?
I don't remember.
Oh, maybe I'm a little older than you. I don't think I'm older than you. But anyway, so there are tons of galaxies out there that are too faint for Hubble to measure its redshift.
And it's asking why.
Right. Now let me tell you why. For the two reasons. One is that the best way to measure a redshift is with spectra, right? And most of the galaxies in the Hubble Ultra Deep Field don't produce enough light to create a measurable spectra that will give you the spectral lines that you need in order to get a good redshift. So most of the redshifts that Hubble has done for the Hubble Ultra Deep Field or deep field images like that are using what we call photographic redshift, okay, in which you take the brightness in several band passes and approximate how that might fit to a typical galaxy spectrum. All right. So if you can get enough photons in several band passes to measure to get a good measurable color in those several band passes. And when I say several, you can do it with as few as 3, but that's not really reliable. You want more like 10. You really love to have like 10 different band passes to get it done well, and that allows you to get a good photometric redshift. So the ones that you don't get enough light to be able to measure it in multiple band passes, you can't get a good redshift. The other things is if this galaxy is so far away that the light in the visible part of the spectrum has been shifted all into the infrared, and there's not much light in the ultraviolet to shift into the visible, you may be able to measure it in just some infrared band passes, but not in any visible light band passes, in which case, again, you can only guess at its redshift because you don't have enough band passes in order to make a good photometric redshift observation.
Okay, great. Good questions, Big New. Thank you. This was from Hydrogen Alpha. Great handle, by the way. 65, 62 angstroms. I know that. Do you think the Hubble telescope, we get this question a lot, so
yes.
Do you think the Hubble telescope will ever find its way inside a museum in the future?
All right, well, let me note that there is a model of the Hubble Space Telescope at the National Air and Space Museum in Washington, D.C. So if you go down to the Smithsonian in D.C., you can definitely see a full-scale model of the Hubble Space Telescope there.
There's another one at Kennedy Space Center at the Atlantis exhibit.
Okay, great. So we have models that are full-scale that you can see. As for the actual hardware ever coming down, I would say probably not. It is just too difficult to bring it down safely. All right. Sometimes we ask, all right, why are astronauts risking their lives to repair Hubble? It's just a science instrument, right? Can't we do the science other ways? Well, the answer is no. We're doing cutting-edge science that can't be underrated. So it's worth an astronaut's life. It's worth the astronauts risking their lives to keep Hubble going. Unfortunately, to bring down Hubble and put it in a museum exhibit, I don't think if I were NASA, I could justify saying, yeah, it's worth putting astronauts in harm's way just to bring it down and put it in a museum. Now, I know everybody, myself included, Tony, everybody I've ever worked with, would love to see it. I can't imagine anybody who wouldn't want to see that Hubble down and the real actual hardware in a museum. But you know, somewhere over the next couple of decades, you're going to have to figure out a way to bring it down safely, either robotically or some other way, such that it won't endanger either people who are going up to get it or those on the ground, because you've got to be able to bring it in a controlled manner.
All right. On that note, we will stop it there. Thank you, Frank. This was a great hangout. We're getting us caught up. Really great stories. So I want to thank you for your time and showing them to us, and thank you guys for your questions and comments. Please check out our hangout tomorrow, where we will be meeting with some principal investigators of people using the Hubble Space Telescope who think they have found evidence of subsurface oceans on Ganymede, Jupiter's largest moon. That'll be tomorrow at 3, and we'll also start it off with some quick tips on the voting for the Ode to Hubble contest. So thank you all for watching, and as always, keep looking up. We'll see you next month.
Whereas the astrophysicist is more the theorist who sits and works on computers and does equations, etc. But we chose that we would introduce ourselves as astrophysicists for one simple reason. No one has ever mistaken an astrophysicist for an astrologer.
Ah, yes. Boy, doesn't that bug you? It bugs me too, and I'm not even an astronomer. I remember
How many times we were at Berkeley, we would get letters addressed to the Department of Astrology.
Yeah.
So the thing is, if you call yourself an astronomer, people sometimes will go, "Oh, I'm a Virgo. What does that mean, huh?"
Yeah. I even get that too. I'm not an astronomer, of course, but I say I work in astronomy, and they do the same thing. They go,
exactly.
"Well, so what does it mean that I'm a Virgo?" And I'm like, I don't know.
It means you belong with a cluster of galaxies.
Yeah. Yes, exactly. So I see the point. Yeah, and you're right, because Neil deGrasse Tyson does do that too. He differentiates himself as that. I always thought it was because it sounded cooler.
It does sound a little cooler, but it also sounds a little pretentious. So I try to use astronomer when I'm with a group that I know understands what the term astronomer means, so I don't sound like I'm pretentious. But for the general public, the term astrophysicist is one that we can use and know that they recognize that, hey, we're a scientist, we're not a pseudoscientist.
Okay, well, we got that out of the way, so there you go, folks. It's all cleared up. Okay, Frank, so I know that you take a lot of time. Judy left a Q&A here. CNN said astronomist in a recent article. What's that? An astronomist, that's right.
Okay.
I've heard that too.
We'll work on that. Thanks, Judy.
Okay, so what do you got this month, Frank? How the voting will go. So that'll be tomorrow. Also going on during the Final Four March Madness stuff that everybody latches on to, we've started our own contest called Hubble Mania, and the link to that is in the description box below. We invite you to vote for your favorite Hubble images, and the winner will be announced sometime, I think, in April 6th to coincide with the Final Four championship. So that's going on also, and we encourage you to play along. The link is at hubble25.org/go/HubbleMania. Finally, with Frank here, I want to invite you to ask us questions and comments and comment to us. We really enjoy the interaction, so we hope you'll leave us questions using the Q&A app. You can also leave comments on Twitter using the Hubble Hangout hashtag. That's what I'm looking at, as well as commenting on the event page on both YouTube and G+. So please ask us questions, and toward the end I will read them out to Frank, and he will get at it because he is an astrophysicist. So let me introduce him. Dr. Frank Summers, welcome back, Frank. It's good to see you again.
Hey, Tony, it's always great to see you.
Yeah, so I gotta ask you real quick.
Okay, go for it.
Astrophysicist, astronomer, which do you prefer?
I actually was just about to do that because you made the point of he is an astrophysicist. Well, so the story is that Neil Tyson and I were up at the American Museum of Natural History, and we were talking about how do we bill ourselves since we are astronomers. I mean, astronomer and astrophysicist are really the same title. All right. If you wanted to split hairs, you might say the astronomer is the type of person who goes out and goes to the telescope and makes observations.
Hello, everybody, and welcome to this month's News from Hubble and Across the Universe with Dr. Frank Summers. My name is Tony Darnell, and I work at the Space Telescope Science Center, and this is another of our monthly chats with an astrophysicist from the Space Telescope Science Institute, namely Frank Summers, who takes a lot of time and trouble each month to gather up some interesting stories, not only about Hubble that involve Hubble, but that are maybe other missions in other areas in astronomy. So before we get to that, though, I have a couple things I want to remind you of. If you are wanting to create a video in appreciation of the Hubble Space Telescope and you want to enter the Ode to Video contest, time is running out. They will close submissions tomorrow. So the clock is ticking if you want to make a video that shows your appreciation from Hubble. The rules are simple. All you've got to do is make a video about Hubble. It has to be less than 3 minutes. Other than that, you can use your creativity. And they have 2 categories for you to enter in. Those under 25, the so-called Hubble generation, you're special because you don't know a world without Hubble. And then there's another category for over 25, and that's the rest of us. And I barely make the cut. I'm right at 26, so I would have to do that second category if I was allowed to enter. So, and also if you entered the contest, you're going to want to join us for tomorrow's hangout. Georgia Bladen, the Hubble social media person at the European Space Agency, is going to join us for the first 10 minutes of the hangout. to show us how the crowdsourcing voting is going to start. It'll start tomorrow afternoon sometime. So you'll want to check that out to learn.
Okay, so news from the universe for March of 2015. All right, so I got to warn you, Tony. We got some cultural references in this month's episode. Okay.
Cultural references.
We're going to have some fun with it. The beginning with the title of our first story is A Series of Fortunate Events.
You mean bad puns? Or what we got?
It's bad pun, but it's also a cultural reference because if you don't happen to know the books, it doesn't really make much sense. So
that was a series of children's books, right?
Yes, it's actually on my next slide. I brought
there
it
you
up.
go.
It's called A Series of Unfortunate Events by the author Lemony Snicket.
Yes, okay, I remember
and
that.
it starts with book 1, which is The Bad Beginning, and finishes with book 13, which is simply called The End. So that's the series of unfortunate events in which all these crazy things happen to this kid. I actually didn't read these when I was a kid. Did you?
No, but my boys did. My boys read them.
Exactly. You know, my kids read through some of them. I know my son read through some of them. It wasn't around. I don't know whether it was around when we were kids. Of course, they must have been around when you were kids because you're just above that age line, right?
Yeah, I'm not quite sure. I mean, I did see the movie when it came out.
Anyway, so that's the book reference, but the series of fortunate events, we're of course talking about the Dawn mission from NASA.
That's right.
An amazing mission that actually went through an amazing number sequence in order to get to the asteroid Ceres. So here is the plot of the series of the various orbits that Ceres was in. All right, and so the first one is the launch in September of 2007. That's 8 years ago, almost 8 years ago. And so that green line here, this is Earth's orbit. And then it moved into this orange orbit that crosses the red orbit, which is Mars. Okay, and it went through a boost from Mars in February 2009. And then it shifted to this green orbit. Okay, and this green orbit is Vesta's orbit, and it went along with Vesta, the asteroid Vesta, for 14 months, and then it shifted to the purple orbit, which is Ceres orbit, where it arrived just this month. So these are the various orbits it was in, and here, by the way, are the transitions from it. So what they did is they added these light blue lines showing where it was thrusting, and then the little brown segments of those light blue lines are when it was coasting. So what you can see is that the Dawn mission has been boosting, has been thrusting for most of its lifetime when it changes orbits. It gets onto these orbits, and then it's almost in continual thrust as it goes in the changes between orbits. And that's actually something that's going to play off important later in the story. So it has arrived at Ceres. So here is a visual inspection of these things. Here is the launch in September 27th, 2007 aboard a Delta rocket. And this is like an amazing shot just after their initial engine burn and you starts to go up off the launch pad. Then in February of 2009, this is an artist's conception of it going past